Hi, guys. Welcome to section C of chapter 12. We're going to continue talking about forces. Okay. So, gravity is one of the biggest forces that we feel on a regular basis. It is a field force that acts between all objects. There's a lot about gravity we don't understand, and there's a lot of really complicated stuff with gravity. That diagram there is showing how gravity actually can warp space-time, and Einstein starts talking about crazy stuff, and my head feels like it's going to explode. It gets pretty heavy, okay? There's this law known as the law of universal gravitation, and it states that all objects exert gravity on each other, no matter what, okay? So if I drop this ball, it's going to fall because the Earth is acting on it with a ton of gravity, okay? And it falls because of gravity. But this ball is also acting on the Earth. This ball is exerting gravity on the Earth. The problem is it's such a small amount we don't perceive it, we don't recognize it. Okay, but all objects exert gravity on each other. The strength depends on the mass, so the Earth has a lot more mass than the ball, but also the distance. Okay, as rockets get farther away from the Earth, the gravity weakens, and eventually the ship can actually break away from the Earth's gravity. Okay, that's when astronauts start experiencing weightlessness. Okay. The acceleration of objects on Earth due to gravity is that 9.8 meters per second squared. The book sometimes uses 9.81 to get a little more precise. That's the rate at which objects fall, okay? Weight, remember, is actually a measurement of gravity. And so while we use pounds to talk about weight, what that's really talking about is mass. We just use the word weight. If we really want to be proper, and measure actual weight, which is the force of gravity, we have to use newtons because forces are measured in newtons, okay? And we can use this equation of force equals mass times acceleration to calculate weight, okay? So we would replace the F with W because the force we're talking about is the weight, which is the force. M is still the mass of the object. And G now is that acceleration due to gravity, okay? So it really is a direct replacement here. Those are kind of filling in for each other, but we've got weight is equal to mass times acceleration due to gravity, okay? So if you look on page 285, we've got an example 12-5 there. It says the Mars rover Curiosity, which landed on the red planet in 2012, has a mass of 899 kilograms. What is Curiosity's weight on Earth? Okay, that's its mass, not its weight. So what is its weight on Earth? Okay, so remember we're going to use W equals M times G. Okay, this is our mass. We know that 9 point, and the book uses 9.81 meters per second squared. That's our gravitational acceleration, so that's our G. Okay, well, W is going to be 899 times 9.81, and that's going to give us 8,820 newtons. That would be that Curiosity's weight on Earth, because that is acceleration of objects on Earth due to gravity. The example goes on to say, okay, but Mars has much less mass than Earth, so its gravity is weaker. The acceleration due to gravity there is only 3.71. That's on Mars, okay? So we'd still use the same mass because mass doesn't change wherever you are. So we'd still do 899 for the mass, but now we would multiply it by the 3.71 to get the weight of this rover on Mars, and that would give us 3,340 newtons. So you can see that things do in fact weigh less on areas that have less gravity. Okay. Moving on, another force we can talk about is friction, okay? Friction is a constant force that works against the motion of objects moving past each other. Whenever two objects touch, they are going to have friction, okay? And it's a force that's actually trying to prevent the movement. You've all experienced this if you've had a rug burn before. The rug is actually trying to prevent your leg or whatever from moving, and so that force is acting on your leg, and it produces heat. That's why it burns. Okay. The amount of friction is proportional to the force holding objects together. So I can very easily slide my hands together. If I push them harder together, if I apply more force, there's more friction between them. Okay, so the harder objects are pushing together, the more friction there will be between them. The amount of friction is also affected by the type of surface. I don't mind sliding on an ice skating rink. I wouldn't want to go and slide on the blacktop because the rougher surface automatically has more friction to it. Okay. There's lots of different types of friction we can talk about. Page 287 shows some of them. One is called static friction. This is between stationary objects, okay, that are attempting to move. So I've got a packet of Post-it notes on top of this book. It's not attempting to move right now. But if I start tipping this book, that packet of Post-it notes is going to want to move. Okay, now it's moving. As long as it's tipping and not moving, that's a static friction. There's enough friction between these two objects that it's preventing them from moving. Eventually, I'm going to tip it enough that the force becomes too great and it overcomes that static friction. Okay. Sliding friction is just the friction between any two moving objects. Okay. Once it's moving, that's sliding friction. You giving yourself a rug burn or a floor burn in the gym, that's considered sliding friction. We have rolling friction, which is where we use like ball bearings or like the ramps on a moving van. Sometimes they have rollers on them. If we can put something between objects that roll, there's just less friction. Okay. Imagine moving a box, a really heavy box across the ground. There's going to be a ton of friction. But if I put wheels on that box, it's so much easier because it reduces the friction. Okay. There's something known as fluid friction, which is basically the resistance as you move through a fluid. Okay. So a fluid is both a liquid and a gas. When you stick your hand out the car window and you can kind of feel it pushing on you, that's fluid friction. When you're trying to like run through the water, that's fluid friction. Okay. And just the resistance that you feel based on that fluid. Friction can be a good thing though. Traction is important. Cars need traction to stay on the road. If your tires are wearing out and it rains, you could hydroplane, you could skid out and be in an accident. So traction increases the amount of friction to help maintain contact. This is why you wear cleats. It just increases the traction so you can run faster. This is why if you've ever played broom ball, it's difficult because you don't have very much traction on the ice. Okay. And then finally, there's ways to reduce friction. Adding oils kind of adds a film. It lubricates between the two surfaces. It reduces the friction. And then those ball bearings, like we talked about. If you have a skateboard, if you look inside the wheels, there's little tiny balls inside there that help the wheels spin very freely. If it's just metal on metal, there's going to be a lot of friction, a lot of wear and tear, and it's just not going to move as freely. Okay. Forces, we've talked about these before. We've got the centripetal force. That's that center-seeking force, okay, pulling something towards the center. And then the centrifugal force, which is an apparent force. It's not an actual force. That's what the object is feeling. Okay, but the real force is that centripetal force pulling something towards the center. Okay. All right. These are kind of cool. Let me move myself out of the way here. There we go. These fundamental forces are the forces that hold all matter together. Okay. And they're a little like hard to really perceive because they're usually not visual. Okay. Gravity is one of them. It's the weakest of the four. We can see the results of gravity, but we can't see gravity itself. Then we have this strong nuclear force, also known as the strong interaction. This one right here. Okay. It's the strongest of the four fundamental forces, and that's what holds the protons and neutrons together in the nucleus of atoms. Okay. Very strong. But then the protons and neutrons are actually made up of particles themselves. And so now we have the weak nuclear force, or the weak interaction, that holds those particles together that make up the protons and neutrons, okay? And then finally, we've got electromagnetic forces that exist between charged particles. And so now we're talking about the electrons flying around the nucleus. And so this is why this has to do with all matter, because all matter is made up of atoms. And so these atoms are being held together by the strong nuclear force, the weak nuclear force, and these electromagnetic forces, which we also see, with sun and other things besides just electrons. Okay, so 4 fundamental forces holding all matter together. That's it.